So for today's session, we'll be doing another technique of integration. So it's called the integration by parts. So if you recall, use substitution or the substitution rule, that particular technique was derived via the chain rule from the differentiation. So for the integration by parts, this is derived from the product rule. Okay? So for example, let f and g be differentiable functions. Then by the product rule, we have f of x times g of x. We get the derivative of that. And we apply left derivative of right plus right derivative of left. So in this case, I have this f of x times g prime of x plus f prime of x times g of x. Okay? So from here, let's just adjust this. Okay, let us try to manipulate this equation. So what we're going to do is to integrate both sides of the equation. So in here, I have the integral of this derivative with respect to x. While in here, of course, I have the integral of this function on the right. So again, on the left, I get the integral of this derivative here with respect to x. And then on the right, we integrate also this sum with respect to x. And then we'll just distribute this integral over the sum. One of the properties of integration, we can distribute it over the sum. And then for this guy here, you have what? Integral of the derivative by the fundamental theorem of calculus, you'll just get the original function. Plus, of course, an arbitrary constant c. Okay? But in this case, I'll just write f of x, g of x. And I am not writing the plus c here. The reason is, on the right-hand side, we still have integrals there. If we actually integrate this guy here and this guy here, they will have all these plus c's, so we can combine them together. Okay? And then, what we're going to do is to put one of the integrals here on the other side of the equation. So, we will obtain the following. So, this is the integration by parts formula. So, we have the integral of f of x times g prime of x dx. This is equal to f of x times g of x minus the integral of g of x times f prime of x dx. Okay? So this guy here, we left it here. Okay? And then this guy here, we put it on the other side. So take note, here it's written g of x f prime of x dx. In here, it's f prime of x g of x dx. They're the same. Okay? So we have this integration by parts formula. And in here, this is indefinite integral. So that's what we have here. And of course, we have the following. If we let u be equal to f of x and v be equal to g of x, then du, this is equal to f prime of x dx. And dv, this is equal to g prime of x dx. So using these substitutions here, we can have the following formula. Okay, this formula here derived from this integration by parts formula for the indefinite integral. So u equals f of x, that's this guy here. We have u here. And then g prime of x dx, that's your dv. So you have here integral of u dv. And then this is equal to, you have here f of x, g of x, that's u times v here. So uv. Minus the integral of, we have the g of x, that's your v, that's the v here, and du, it's f prime of x dx, this guy here. Okay? So why did I introduce this? This is actually the one we are going to write all the time when we do the integration by parts. Okay? Of course, originally you don't see this G prime or F prime in here. You'll just see what? You'll just see product of functions, possibly. Okay? So given the products of function, you have to identify which will be the U and which will be, in this case, the dv. Okay, you have product of functions. Okay, one of the functions or combination of functions there will become your U, and then the rest of the function times the dx, okay, times the dx, that becomes your dv. Okay, and once you have identified U and dv, you can now apply this guy here. You can now apply this formula in here. Okay? For the definite integrals, of course, you just need to evaluate. If you integrate from a to b, f of x g prime of x dx, that's equal to f of x g of x, evaluated from a to b, minus the integral from a to b of g of x f of f prime of x dx. Okay, so you'll just put the evaluation. Okay, are we good so far? So, how is this helpful to us? Look, the main goal of doing this integration by parts is to provide a new integrals that will be easier to evaluate. You might ask, sir, on the left-hand side, you have integral, and on the right-hand side, you have another integral. So, what's the point? Well, possibly, this integral on the left-hand side, it's not easy to integrate. Okay? And then, your goal, when you apply your integration by parts, you need to produce this expression such that this guy here, this integral here, is easier to integrate. Okay? But how do you do this? Again, you have products of function in here. You have the function f of x, you have the function g prime of x, and of course, you wouldn't know which one is the g prime of x immediately or which one is the f of x there. What you see are just products of functions. Okay? So your mini goal is to choose properly which will be your u and which will be the dv here, because you have u dv. Okay? And in choosing that, you have to think that when you choose your dv, it should be integrable for you easily. Because your dv, it is equal to g prime of x dx. You want to produce the v from your dv. You want to produce the v from the dv. And if you have dv, you need to integrate that in order to get v. So you need to choose carefully what the dv is. Once you have the dv, you know how to integrate that easily. You will be able to get the function v. Of course, if you have any function f, you can easily differentiate that. And why do you have to differentiate that? Because you will have to produce this guy here, v du, and du it's the derivative of the u, which is the derivative of f. Okay? And then the second part of your mini goal is, does this part here, does this integral here, v du, easier to be integrated? Okay? Or is this integral here easier to be integrated? So you have to keep in mind those goals. Okay? Now, I'm going to tell you another hint in choosing your U and your V or the DV. Okay? We call that this liate. Okay? So what is this? You have L, I, A, T, E. Okay? L stands for logarithms. I stands for inverse trigonometric functions. Okay? So logarithms, of course, that's just ln or log base log or log base 2, etc. Most of the time, we'll be using ln. Inverse trig, these are your tan inverse, sine inverse, okay? Cosine inverse, etc. A here, this is algebraic, okay? Algebraic. What are these? These are your polynomials, okay? These are possibly square root of x, okay? Or maybe 1 over x, okay? These are, actually this 1 over x, this is not algebraic. So we do not include that. Okay? So polynomials or radicals, okay? Okay? Etc. And then you have t. You expect this is trigonometric functions. Okay? Trig functions. So you have your sine, cosine, tangent, etc. The other three, cosecant, secant, cotangent. And then your e here, these are your exponentials. Okay? E to the x, 2 to the x, etc. Okay? So these are the family of functions. L, logarithms. I, inverse trig functions. A, algebraic. T, trigonometric. E, exponentials. Liate. Remember that. Okay? And so what? Oftentimes, you will see this when you need to apply integration by parts. Okay? This f here will belong to one of these. Similarly, this g here will belong to one of these. Okay? So you choose your u. Okay? This is the function. Okay? The function which belongs to the family. So the function which belongs to the family that comes from this list. Okay? The family that comes first from this list. That comes. So the function which belongs to the family that comes first in the spelling. Okay? And of course, the remaining function will be your dv. Okay? So for example, if you have a product of logarithmic and algebraic, okay? For example, you have polynomial x and then ln. So x times ln of x dx. We will do that later. Okay? Ln belongs to the logarithmic function, logarithms, okay, logarithmic functions, and it comes first before the algebraic. So your u will be the ln of x, and then the dv will be the x dx. Okay? Is this clear here?
So, sir, if, for example, we have a function, it's like find the antiderivative of ln of x e of x dx, then ln of x is ru?
Yes. Based on this, your u will be the ln of x, okay? And then your dv will be the exponentials. That is correct.
Perfect. Thank you, sir.
You're welcome. But here's a warning. Not all combinations work. Okay? Not all combinations work. Even if the two functions, each of them belongs to one of these, okay? Possibly the combination won't work, in a sense that your integration by parts won't work. It's still hard to integrate. That's what I meant. And possibly you need another technique. Okay? A lot of students struggle in this. I must say. Why? Every time they see an integral, if they can't use substitution, they will just use integration by parts, follow this, and in the end they will not be able to answer it because it's not actually solvable using integration by parts. Okay? So of course you will have some hints. You have this, and um, you can choose your u easily, but you have to also know when when to um, when to stop using the integration by parts. You could try once, okay, and then maybe try again um, another um, another choice for you or DV. Okay, if it fails maybe 3-4 times, then possibly you need to use other techniques. Okay. Now, if you have your notes, there are 9 examples there. Okay, so we will solve all of them. Okay, so let's start. First, we have here integral of ln of x. Okay, by the way, um, if you look at this integral here, you have integral of u dv. When you choose your function u, the dv is everything else. The dv must include the dx. Because dv, it's a differential, so it must be in the form of differential. There must be a dx there. Okay? So, in here, again, we want to integrate ln of x dx. Okay? So, as you can see, it looks like there's only one function here. Actually, there's only one function in here, just the ln of x. But you can think of this as 1 times ln of x. 1 here, this is a polynomial, this is algebraic. Okay? So from your Liate, your u will be ln of x, and the dv, okay, let me write dv here. The dv will be 1 dx. I'll just write dx. Okay? Yes, question?
Yeah, I was just wondering, is there a quiz today?
Uh, no, I did not announce any quiz.
Okay, perfect. Thanks.
Okay. So you have here u equals ln of x, dv equals dx. Okay. We need du we need that du. So we'll just have the derivative of u. But the derivative of u, it's just the derivative of ln of x. This will be 1 over x dx. Okay. And here, you have dv equals dx. Okay. If you integrate this dv, okay, you'll just get v equals x plus c. Okay. Which means, what do? We now we now use this. So integral of ln of x dx, this is u times v. So we have ln of x times x plus c. Okay? Minus the integral of v du. Okay? So you have the integral of v, which is x plus c. Du, it's 1 over x dx. So 1 over x dx. Okay? And then, look at this. We can simplify this guy here. This guy here. Let's just distribute that 1 over x over this sum here. Okay, so you will have equals ln. So also let's distribute this ln of x over the sum x plus c, so that we will see that we have x ln of x plus c ln of x. And then in here we have integral. If we distribute this is just 1 plus c over x. And if we integrate this, we will have x ln of x plus c ln of x. We integrate 1, that's just x. So minus x. We integrate c over x. The integral of 1 over x, it's just ln of x, correct? So you will have here minus c ln of x plus the arbitrary constant again, coming from this guy here. Now notice, you have here c ln of x minus c ln of x. Take note that the c here, they are the same. It's from your x plus c. This is x plus c. So this c here is the same as this c here. So if you simplify this, you'll just get x ln of x minus x plus c sub 1. And this will be your final answer. So this is your integral of ln of x dx. Okay? Yes, question?
Couldn't we just add C at the end?
Yes. Actually, yes. Take note that in here, you are differentiating or you are integrating.
Mm-hmm.
So when you integrate indefinite integral, you'll have the plus c, technically. Okay? Now, you can actually prove that this plus c here, you can take it to be equal to 0. Why? Because all the time, for example, like this guy here will always cancel this part here. All the time. Okay? This guy here will cancel this guy here. Whatever, when you were able to do this integration by parts, which means that this c here can always be taken to be c equals 0, the c coming from the dv. Okay, so I'll put that here, note. Okay, c, so observe there is c ln of x minus c ln of x. Okay, this always happens. This always happens, meaning the cancellation. This c plus something minus c this c times something minus c times that same thing. Okay, this always happens. So in the dv, okay, in the dv here, we can take
Tu vas
c
t'occuper
equals
parfait.
0.
Alizée, elle n'aime pas le ton de ce qu'elle m'a dit. Je sais pas si elle n'aime pas ou elle peut pas en manger. I don't remember. Mais elle n'est pas trop de ton. Du coup, amène une quantité pour nous deux.
Sorry about that. Okay. So are we clear? So when we do this, the dv particularly, we can always drop the plus c. We can always take it to be 0. So we'll just need x. Okay? Are we good? We can prove this here. We can prove this. So I said here, this always happens. So in the dv, we can take c equals 0. In fact, we can prove that. Okay? Because, for example, if you have your b plus c instead of b, okay, instead of v, okay, what will happen to the integral? Integral u dv, this is equal to u v plus c minus the integral of v plus c du. Correct? So if you distributed this, you have uv minus plus cv, and then in here you will have integral of v du minus also the integral of c du. And this guy here, this is minus cu. Or, sorry, why is this cv? This is cu. This guy here is cu. So you see, after integrating this cdu, you'll get the cu. And this cu will cancel this cu here. So it's as if we don't have the plus c. Okay? That's a very good observation, by the way. Other questions? So we want to integrate this t ln of t dt. And notice you have here logarithmic. And then, so I'll use capital L instead. This is your capital L. And then the other guy, of course, the t here, it's polynomial, so it is algebraic. Therefore, we expect to use u equals ln of t. And dv, that's the other function. You have here t dt. So Again, du, that's 1 over t dt, while v, this is t squared over 2. Therefore, we will have uv, okay, uv. So that's ln of t times t squared over 2. So I'll write t squared first before ln of t divided by 2 minus the integral of v, which is this guy here, t squared over 2 du. That's 1 over t dt. And let's just simplify this guy here. So we rewrite t squared ln of t over 2. Then minus. Let's bring out the 1/2 here. Okay. Then the integral of t dt. And we now integrate this. You have t squared ln of t over 2 minus 1/2. This is again t squared over 2 plus the arbitrary constant c. Or we can now have t squared ln of t over 2 minus t squared over 4 plus the arbitrary constant c. So this is the final answer. Okay? Next problem here. We have integral of w cosine w dw. So for this, you have w, again, polynomial, that's algebraic. And then you have cosine w. This is trigonometric. Remembering the hint, Liate, algebraic comes first before trigonometric, which means this time our u will be w. And then your dv will be cosine w dw. Okay? Now, du will just be dw, the derivative of w, it's 1 dw. While this guy here, if we integrate this, v will be sine of w. Okay? Therefore, if we do this, you have uv, so this will be w sine w minus the integral of v, this is sine w, du, which is dw. So we have sine w dw. So in here, we have w sine w minus. We integrate sine w, that is negative cosine w. And then you have the plus c. Or you will have w sine w plus cosine w plus c. So this is the final answer. Okay? Very good to the student who wrote the answer in the chat room. Well, sent the answer to me. That's nice. Okay? Now, as you can see, every time we have the integral of d du, we always have nice function to be integrated. Remember, that is one of your mini goals. Make sure that this guy here is integrable easily. Okay? If this guy here becomes more complicated compared to your original integral, then most possibly the integration by parts method you use fails. So you have to choose another u and another dv. Okay? Next, integral of t squared e to the t dt. So in here we have the algebraic. So I'll write a. And then here you have the exponential. So again, remember liate, but that means u will be t squared. And then dv will be e to the t dt. Now, for this, I'll write subscripts. I'll write this u sub 1 and then v sub 1 here. You will see later why. So for this, we'll have du sub 1. This is equal to 2t dt. While here we have v1, this is e to the t. So if we apply integration by parts, you have u1 v1. So that's t squared e to the t minus the integral of v1 du1. So you will have here e to the t, and then you have here 2t dt. Okay? Now look at this. Originally, we have t squared e to the t. After applying integration by parts, we have here 2t e to the t. This 2, it's just constant. It goes out of the integral. What you have is t e to the t. But notice, from power 2, it became power 1. Okay? So this guy is easier to integrate than this guy because you are reducing the power of t, particularly of the polynomial. Okay? So if you think of it, if you try to integrate this again using integration by parts, possibly the t will disappear. And you'll just have maybe the exponential function. Because, well, from here, I still have the e to the t. Okay? So maybe the e to the t will still be there. But more importantly, from t squared, it becomes 2t, or you have power 1. So maybe when you apply the next, when you apply integration by parts, the next one will have power 0, which means it will disappear. Okay? So here, we apply again integration by parts. And that's the reason why I used u sub 1 and v sub 1. Because I will apply again a second integration by parts. And notice, this is still exponential. This is still algebraic. So same pattern. Your u sub 2, let's just write t because I'll factor this t, this 2. I'll bring it out outside the integral sign. So u2, that's e to that's t dv2 this is still e to the t dt. And then du2, this is equal to 1, or this is dt actually. And then v2, this is still e to the t. So here, this one, we're good. We have here t squared e to the t, and then minus 2. Okay, quantity. Take note of that grouping. Don't forget. You integrate t e to the t dt, so you have u, v, or u2, v2. That's t e to the t. Minus the integral of v2 du2. And you will have e to the t dt. And then this guy here, you can easily integrate. So observe that the polynomial here, it's just 1. So from power 2, we got power 1. Now we got power 0 here for the polynomial. So this guy here, it's t squared e to the t minus 2t e to the t. And then if you integrate this is still e to the t. So plus 2 e to the t, and then you have the arbitrary constant c. Okay? Questions so far? Yes.
Yes, sir. So the reason you did like the u1 and u2 is because the second integral is still too complicated.
Yes, it's still quote unquote complicated, but it's less complicated compared to this guy.
Okay.
And that's the reason why we thought maybe integration by parts can still be used.
Okay. All right.
Yeah.
Thank you.
You're welcome. Okay. Other questions? Next.
Sir, can you go back for one more second, please?
Okay.
Thank you, sir.
All right. Next. Integral of e to the 2s sine S ds. So in here, we have trigonometric. Here we have exponential. Okay? So liate, trigonometric first before exponential. So our u here, this is equal to sine S. And dv here, this is equal to e to the 2s. Oops, I forgot the ds. Don't forget the differential or the ds. Now, again, I will put subscript. This is u1, this is v1. So you expect I will apply again integration by parts later. Okay? So here du1, this is equal to, so derivative of sine S, that's cosine S ds. v1, if we integrate this, okay, this will be e to the 2s over 2. Okay? Are we good with that? You actually need u substitution for this. You take u be equal to, or the substitution rule. You take u to be equal to 2s, and then du will just be 2 ds. So your du is, your du1 half equals ds. So you have to use u substitution from dv1 going to v1. But this is it. Okay? So now we apply integration by parts with this pair, okay? With this pair u1 dv1. So u1 v1 will get sine s e to the 2s divided by 2 minus the integral of v1 du1. So we will have e to the 2s cosine s ds, and there's the 1/2. So I'll put the over 2 in here. Later, I will bring it out. If you look at this, so originally we have e to the 2s, and then we have sine s. After applying integration by parts, I have now e to the 2s and then cosine s. But sine s and cosine s, they are practically the same. Okay? Sine s, it's just cosine s with the movement, maybe pi over 2 shifts to the left or to the right. They are practically the same. That's sine s and cosine s. Which means the difficulty of this is just the same as the difficulty of this. Now, when this happens, okay, most of the time, this happens when the combination is exponential and trigonometric. In fact, exponential and sine and cosine. Okay? This happens when you have exponential times sine or cosine. If you have this, carry on. Just integrate this again using integration by parts. And using the technique that you use, the same technique. You have exponential here, you have trigonometric here. So we will have u2 equals cosine s dv2. This is e to the 2s ds. And again, the over 2, I will bring it out. Okay, I will bring it out. So for this substitution, we have du2, this is equal to, so in derivative of cosine s, that's negative sine s. While for v2, the same as seen above, e to the 2s over 2. Therefore, we have here e to the 2s sine s over 2 minus 1/2 quantity uv. Okay, we have the subscript here, but anyway, uv. So we will have e to the 2s cosine s divided by 2. Then minus the integral of v du. You will have e to the 2s over 2, but I'll write that later. So times negative sine s over 2. And then, of course, I have the ds here. I'll just adjust. Okay. So sine s, we have the sine s in here, and then the ds, and then we close the parenthesis. Now let's try to simplify this. This guy here, okay, we will have e to the 2s sine s over 2 minus e to the 2s cosine s over 4. And then here, this becomes plus. Actually, this is still minus. Why? There's a minus in here. Look at this. There's a minus in here. There is a minus in here. So it becomes plus. But there's a minus all the way outside here. So we still have minus. But anyway, we will have 1/4 integral of e to the 2s sine S ds. Okay? Any questions so far? Yes.
I'm a bit confused about what you did with the integral e to s cosine s over 2.
This guy here
From that step to the second step,
to this step.
you put 1 over 2 outside of the integral, and then
This guy here, yes, we put it outside.
So what?
And then we apply this.
So wouldn't you have e to the s cosine s minus the integral of?
No, e to the 2s. You have the over 2.
Oh, right, I forgot. Okay.
Yeah, you still have the over 2 in here.
Okay, thank you.
You're welcome. Okay, so good. So far, so good. Now, you look again at the integral here. We have negative 1/4 integral of e to the 2s sine S ds. Sir, that's the original integral that we have. Yes, that's the original integral that we have. We were able to bring back that original integral. And furthermore, if you look at this, the coefficient of this integral, it's 1. The coefficient of this integral on this side, it's negative 1/4. What I'm saying, they don't have the same coefficient. On the left-hand side, the coefficient of the integral, it's 1. On the right-hand side, the coefficient is negative 1/4. They don't have the same coefficient, meaning they will not cancel. Meaning, we can combine them. Okay? So what does this mean? This means we will bring this to the left-hand side. We will bring this negative 1/4 integral of e to the 2s sine S ds. Bring it to the left-hand side. So we will have integral e to the 2s sine S ds plus 1/4 integral of e to the 2s sine of S ds. And then on the right-hand side, we just have this. We don't have any integrals. Okay? Are we good? So this is now equal to e to the 2s sine S over 2 minus e to the 2s cosine S over 4. I'm not putting the plus c yet because I'll have to simplify this, and I'll put the coefficient, the last coefficient here to the other side. That's the time I will do the plus c. Okay? So again, adjust. So what will happen is that I have here this plus the 1/4. That becomes 5/4, correct? That's just 1 plus 1/4. So I will have 5 over 4 integral e to the 2s sine of S ds that's equal to this same guy here. Okay? That's equal to this same guy here. So we'll copy e to the 2s sine s over 2 minus e to the 2s cosine s over 4. Then finally, all we need to do is to multiply everything by 4 over 5. So this will be cancelled, and then we will multiply the 4 over 5 in here. And then you just put the plus c. So again, technically, you will have the plus c in here, in this part in here. You can put that. Say you put plus c sub 1. And then once you multiply the constant, that's the time you put plus c instead of plus 4/5 c sub 1. So anyway, therefore, integral e to the 2s sine S ds. So we multiply by the reciprocal of this. When you do that, you'll just have 2 e to the 2s sine s over 5 minus e to the 2s cosine s over 5 plus the arbitrary constant c. So this is the final answer. Okay? Yes, question?
Yeah, I just don't understand what happened after negative 1/4 times integral of e2s sine s ds.
We bring this to the other side of the equation because this guy here, it means this guy equals this guy, correct? This is the left-hand side. This is the right-hand side. So we bring this guy here to the other side of the equation. So this guy and this guy will be both on the left-hand side. That's why it became plus.
All right, yeah.
And then you just add these two guys. It's like you have one in here. So 1 of this plus 1/4 of this, that becomes 5/4.
Okay, I understand.
Okay,
All right, thank you.
you're welcome. Other questions? Okay. So again, this guy, this technique here, it happens when you have the exponential and the sine or cosine. But it also happens to other situations. Okay, not just this guy here. It also happens to other situations. Next. Now we have the integral from 0 to 1 of tangent inverse x dx. So in here, what I'm going to show you is a combination of integration by parts and substitution rule. The solution for this needs integration by parts first, and then later you'll have the substitution rule. So we use integration by parts first. Look at this. Again, it looks like there's only one function here, but there's a 1 here times 1 in here. So it's an algebraic. But then, 1 is the algebraic. This guy here, it's inverse trig. Correct? Which means that I, this guy here, should be the U. Because 1 is algebraic, I comes first before A. So in here, U equals tangent inverse of X. dV, this is equal to the remaining 1 times dx, or let's just write dx. Now, du, this is equal to 1 over 1 plus x squared dx. And v, that's just x. So in here, u times v, that's x tangent inverse of x evaluated from 0 to 1. Take note, it's still definite integral. And minus the integral from 0 to 1 of v du. So we'll have x over 1 plus x squared dx. And you observe this. This is where you apply substitution rule. So let's do substitution rule in here. I already used this variable u. So instead of u, I'll be using, say, t. So t equals 1 plus x squared dt. This is 2x dx, or I have dt over 2. This is x dx. And then when x equals 0, the value of t will be 1 plus 0, which is just 1. And when x equals 1, the value of t will be 1 plus 1, which is equal to 2. So in here, I will have x tangent inverse of x from 0 to 1 minus the integral lower limit of integration, that's 0. So the corresponding value, it's 1 for the variable t. Upper limit of integration, that's 1. The corresponding value for the variable t, it's 2. And then I have x dx here, x dx in here, that will become 2 dt over 2. Okay? So we have that dt over 2. And then I have 1 over 1 plus x squared. T equals 1 plus x squared, so this is just 1 over t. Okay? Okay. So there's a question. With u substitution, the limits will need to be changed according to u, right? That is correct. But look at this. I am not really using u in that quote-unquote u substitution. I'm using t. That's why I don't call it u substitution a lot of times. I call it substitution rule because I can use any variable. I can use v, I can use s, I can use w. It's just that you are used to using u substitution. I mean, you are used to using u as your substitution variable. But that is correct. If you use u in your substitution rule, then it must be according to u. In here, I am using t. So I also use t in here. So let's finish this. You have at x equals 1 for this. This is 1. And then you will have tangent inverse of 1. So let me write that tangent inverse of 1. And then at 0, well, you have here x equals 0 and tangent inverse of 0, that's also 0. Okay, so tangent inverse of 1 minus 0, let's just write tangent inverse of 1. On the other expression here, we have here 1/2. And then we integrate dt over t. That's just ln absolute value of t. We evaluate this from 1 up to 2. And this is equal to what? Please recall tangent inverse of 1. That's pi over 4. It's a special value, so I hope you remember that. And then here we have minus 1/2 at t equals 2. We have ln of 2. At t equals 1, we have ln of 1. But ln of 1, that's equal to 0. So all in all, you will have pi over 4 minus ln of 2 over 2. So this is the final answer to this expression here. Okay? All right. You are raising your hand, Cheyenne, no? Or that
Yeah,
was
sorry,
already?
I forgot. I
Yeah,
forgot.
okay. Any questions? So again, this is a combination. You have integration by parts, and then you also do substitution rule. Okay? Next problem here, we have integral from 1 to 2 of z squared ln of z dz. I'll just skip this because this is similar to the first two problems that we had. So I'll ask you to work on this. This is now a definite integral, so don't forget to evaluate the definite integral or evaluate at the limits of integration. So we move to our next problem in here. We have integral of e to the square root of x dx. Okay. Now, for this, we will also use combination techniques. Also, integration by parts and substitution rule. But this time, we will start with the substitution rule. Okay? So, how is this done? In here, we can let u be equal to e raised to square root of x. Instead of u, I'll be using t. Because again, I will use integration by parts, and I'll be using u and v there. So I'll be using t in here. Now, dt, this is equal to what? So derivative of e to the square root of x. Okay? We have e to the square root of x. Then by chain rule, we multiply this by 1 over 2 square root of x dx. Note that I only have here e to the square root of x dx. I have the e to the square root of x here, I have the dx here, but I also have this 1 over 2 square root of x. So what we're going to do is to rewrite this square root of x in terms of the variable t. So notice that in here, okay, t equals e raised to square root of x. This implies that ln of t, this is equal to square root of x. Okay? So this guy here, we can rewrite this as 2 square root of x dt equals e to the square root of x dx. But square root of x, it's ln of t. So we will have 2 ln of t dt equals e to the square root of x dx. Which means that this guy here, this is simply integral of what? I have here e to the square root of x dx. This will be this guy only. 2 ln of t dt. That's our substitution rule. Following so far? Now, look at this. 2 ln of t dt. We solved this in our first problem. And we used IBP. So, we used IBP, integration by parts, okay, to solve this. To solve this. So, see example 1. Okay? So, let's go back to that first example and just copy the answer. Anyway, we've solved that. So, it's this guy here. Integral of ln of x dx, that's x ln of x minus x plus c1. So remember this, x ln of x minus x. It's not this, it's this guy. Therefore, this guy here, this is just 2 t ln of t minus t. And then you have the, let's put the arbitrary constant outside here. Okay? And then you now bring back the original variable x. So this guy here equals 2 times t, it's e to the square root of x. And then you have ln of e to the square root of x. And then minus e to the square root of x plus c. And this guy here you can simplify. Ln of e to the square root of x, that's just square root of x. So you will have 2 times square root of x e to the square root of x minus e to the square root of x. And then plus c. So this is the final answer. Okay?
Sir?
Yes.
Yeah, why is the square root of x equal to ln of t?
Because of this. That's the actual property. You have t equals e to the x. If you get ln of both sides, you also get ln of e. raised to square root of x, but that's precisely this guy here,
Oh, okay, okay.
which is square root of x. So the property, so you have here, for example, yeah, let's just write that. E equals e to the square root of x, you get ln of t. This is equal to ln of e to the square root of x. And your laws of logarithms, this is square root of x ln of e. Ln of e, it's 1. So you have here square root of x.
Okay, thank you.
You're welcome. Any questions? Okay. Now, in the exam or homework or quiz or final exam, if I ask you to integrate this, of course you will end up, or you will possibly end up, excuse me, you will possibly end up with this guy. You have to calculate this. Do not write this was solved in the exercise. No, do not write that. Of course, I want to see how you're going to solve it without looking at the notes. Okay? So you have to solve this. You have to use your IBP and eventually give this final answer. Okay? If in the exam I ask you to integrate t ln of t dt, you won't say using example number 2 in the lecture, this is the final answer. No, you have to show the steps. Okay? Any questions? Let's have this. Integral of x ln of 1 plus x. It looks similar to what we did. In fact, it's very similar, except that here we have ln of 1 plus x, not just ln of x. So we have to adjust this. And again, we will combine substitution and then IBP. So for the substitution, we can let t be equal to 1 plus x dx, or dt equals dx. Okay, dt equals dx. But here we have an x here. Your x is simply t minus 1. You just bring this 1 to the other side of the equation. Which means that this guy here, this is now the integral quantity t minus 1 ln of t. And then the dt. Or here, we have integral t ln of t dt minus the integral of ln of t dt. And then again, this is example 1. This guy here, example 1. This guy here is your example number 2. So you can go back to that and then solve or write the final answer for this lecture. But if this appears in the exam, you have to solve completely. You have to show the steps. Okay? So continue from here. Questions so far? Okay. So this is the last example for our lecture. Okay. But I will teach you one more technique. Particularly if you have something like this. So a technique used in the in integrating using integration by parts. Okay. This technique is used if you have a similar type of integral, just like this. Okay? Let us try to resolve this or recalculate this. Now, this technique, okay, can be used if you have the following combination. You have here polynomial times either sine, cosine, or exponential. So one of the functions is polynomial. The other function, it could be sine, it could be cosine, it could be exponential. So in this case, you have here polynomial and then exponential. Okay? When we solve this, we use integration by parts twice. This method is the shortcut for that integration by parts twice, or even thrice or 4 times, okay? Depending on the polynomial. We call this the tabular method. So, tabular method. So, what is this? You have u and you have dv. Okay? Of course, the u, what you're going to do is you differentiate this. So, derivative. Okay? While the dv, you integrate. So, here, derivatives. So, you're going down there. For the dv, you integrate. Since you have your polynomial, this is algebraic, correct? This guy here, it's algebraic. For this is either trigonometric or exponential. In any case, algebraic comes first. So the u will always be the polynomial. Okay? Let's use this example. So you start with that polynomial, you have t squared. What you do is to differentiate this until you reach the 0. This is polynomial. There will come a time that the derivative will be 0. So differentiate, you have 2t. Differentiate again, you have 2. Derivative or differentiate again, you have 0. Of course, for the dv, you either have trigonometric or exponential. In this case, we have e to the t. We integrate. Okay, we integrate. We still have e to the t. Make sure on first step, or you copy on the first row here, on the first steps, they must be aligned. Second steps must be aligned, etc. And you will stop integrating once the 0 has its partner here. So integrate again, and then integrate again, and we stop because this is already the partner of that 0. But actually, this is not the partner of 0. Okay? In essence. Why? When you have this, you put this alignment. Okay? From the derivative, you align it with the lower, so one step lower integral. So from t, one step lower integral, e to the t. You have the 2t, one step lower in the integral. 2, one step lower in the integral. So even if you continued integrating in here, for instance, you have e to the t here, that is the actual partner of 0. And it's just 0. So that's why we stop once the 0 has a row partner, quote unquote row partner. So they are on the same row. Okay, following so far? Once you have this, you now write signs alternately starting from positive. Positive, negative, positive. So in here, you have positive. Here you have negative. Here you have positive. So when we write here positive or negative, it means positive 1 and then negative 1. So what do? You multiply those guys. Okay? You multiply the partners, this type of partnership, with the positive 1 or negative 1, depending on what will appear in here. So alternate in signs starting from positive. So what I'm saying is you multiply t squared times 1 because that's positive 1. So t squared times 1 times e to the t. So that's your t squared e to the t. And then next, you have 2t times negative 1 times e to the t. That's negative 2t e to the t. So negative 2t e to the t. Here, 2 times positive 1 times e to the t. That's positive 2 e to the t. And then you have your plus c in here. This is the answer that we obtained in here. T squared e to the t minus 2t e to the t plus 2 e to the t plus c. That's exactly this one. Tabular method. And this is actually continuous application of integration by parts. Remember, UV or UDV. When you integrate this becomes V. So UV. Okay? And then this is now your new U. This is now your new V. Your new DV. If this is your new DV, this becomes V. So UV again. And then this becomes your new U. This becomes your new DV. You integrate again, this becomes your V. So UV. Okay? So it's just continuous application of integration by parts. Okay? So again, this works on this type of combination, polynomial times sine x or the sine function, or polynomial times the cosine function, or polynomial times the exponential function. By sine, cosine, exponential, you can have sine 3s, you can have cosine 5s, or e to the 2t, or e to the 5t. It can be anything. Okay? But not, okay, but not sine squared s. It won't work there. Okay? Not cosine raised to 5 x. It won't work. Okay? you just have something like this, sine, and then the argument, 3s, 4s, etc. Okay? And then, again, so you have those combinations, you write u, you write dv, the u, you start with the polynomial, and then the dv, whatever is the other function. You get the derivatives for the u until you reach 0. You integrate the other function until the 0 has a row partner. Once you have that, give the partnership. You have the u, you partner it with the dv lower. Okay, one step lower. So if this is your u, this is the dv, one step lower. Okay, so it's like you slide one step lower. And then you write plus minus alternately, starting with the plus. And then lastly, you just multiply all of that. The same line here, including positive 1 for plus or negative 1 for minus. And that will be your final answer. Okay? Now, again, for the types of sine, cosine, and exponential, it should be something like this only, the simpler ones. You don't have sine squared. You can't have that. You will not be able to solve it as of this moment. We will have a different technique. Next, are we allowed to use this method in the exams and tests? Yes, you are allowed to use this because this is basically integration by parts. And you are applying integration by parts here. So you can use this method.